Hi, good morning to everyone. First of all, I want to thank Pablo Levy for giving me the chance to show my work, to share my work with you. Okay, I'm going to talk today about the phenomenon of stochastic resistive switching. Is it working? Okay, this is the outline of my talk. First, I will introduce the motivations of my work. Then I will present results in a simple model of the memristor. Then I will show you some experimental results. After that, I will present a more complex model of the memristors. And finally, I will discuss my conclusions. So, as we all know, the storage density is driven by the Kreider's law, and higher circuit densities lead to a smaller signal-to-noise ratios, and hence to a more prominent role of noise. So, one of the proposed alternatives for succeeding current storage devices is the ReRAM technology, and we are interested in studying the influence of noise on these devices. So, in 2008, Strukov presented a very simple model of the memristor, and recently Stochastic and Devendra showed that for internal noise, for instance, thermal noise, leads to higher contrast between the high and the low resistance values. So, these are the equations of the memristive device. Here is the equation for the state variable, and this is the equation that relates the voltage and the current. So this model consists of two in-series resistors whose net resistance depends on the position of this barrier. This barrier separates one doped region from another undoped region. This is the motion of this barrier is given by this equation, and in this model the resistance has a linear dependency with the state variable. As usual, we define the EPI ratio, the electric pulse induced resistance ratio, as the relative difference between the high resistive state and the low resistive state. Here we have a picture of the apply of the driving signal. Here we have a pulse, a positive pulse to set the memory, the state of the memory. We measure the resistance here, then we reset the memory and measure the resistance here. And then we calculate this ratio. Here we have the results.
Before you go on,
yes.
Go back to the previous one. Can you motivate a bit more the first equation, that was the 4x on my oxides and something?
This equation?
Yes.
Yes, this equation takes into account the motion of these ions by an electron, by an external electric field. And this nonlinear part takes into account some nonlinearities observed and reduces the velocity when the barrier is approaching to the borders of this sample. Is what Stochastic presented. Strukov. Yeah. Well, here are the results that Stochastic and Devendra show that there is an optimum amount of noise that maximizes this ratio. On the other side, we didn't find this effect when external noise is considered. In this case, we have an additive noise, so the influence of noise is independent on the state variable. In the other side, we have multiplicative noise, and the influence of noise is strongly dependent on the state variable. So we wanted to check this result with an experiment. We conducted the experiment on a manganite sample, the LPCMO, with hand-painted silver contacts. We apply the current pulses between contacts A and C, and for instance, we measure the resistance between A and B. This is a picture of the applied signal. We apply noiseless and noisy pulses with some mean value. Then it was generated via computer software, and then we apply it with an acquisition board. Then we rate the resistance state. We measure the resistance state by applying a small bias current, and then we apply a pulse with a different mean value. The same, for example, the same noise intensity, but a different mean value. So, as expected, when noiseless pulses are applied, here we have the hysteresis loop. We range from minus 800 to 800 milliamperes, and we can see the hysteresis loop. Then we apply we lower the amplitudes of the applied current, of the applied pulses, and we didn't see the effect of the resistive switching. I think that's expected. But when we take into account the addition of noise on each pulse, we can see a hysteresis loop again with these values of resistance similar to those obtained when we apply large input pulses.
So, which is the magnitude of noise?
In this case, was in the order of the standard deviation of the noise was in the order of 100 milliamperes. Current noise, yes. So we look at the bibliography for a model that could take into account this effect. Yes, in this case, in this model, no. To the current, yes. So we move to a model proposed by Pickett and colleagues. This model consists of an effective tunneling barrier in series with a bulk resistance. The total resistance depends on the width of this barrier, but in particular, we use a simplification introduced by Batinsky and colleagues of this model, where here we have the state variable equation, the state variable motion equation, and we can see that it has a threshold for the current. Here, these parameters have the opposite sign, so the sign of the velocity of the width, or the change of the width, will depend on the current and the position between the position with the thresholds. In this model, the resistance has an exponential relationship with this state variable. So here we have some.
Sorry, this is important. One phrase in the previous lecture. Where does the exponential factor come from? Remember we discussed that in the Pickett
Yes, this.
And so whenever you show an exponential, then maybe this is where it is getting the answer.
In this work, what they did was to fit the results of Pickett. So these are filling parameters. I don't know if they had a physical motivation. Okay. Sorry, I don't have the answer. So with the red line are numerical results. When large input pulses, we have this contrast. Then we lower the amplitude, and we have this contrast. Then we apply noise to the pulses, and the contrast is large. We turn off the noise, we have the same behavior as before, and when we turn on noise again, we have a similar behavior. The squares are the experimental data. So we found a very good agreement between the measures and this model. So we study the dependence of the pi ratio as a function of noise and for different input amplitudes. And we found that when small input amplitudes are applied, there is an amount of noise that maximizes this ratio, so we have a better contrast. But when large input pulses are applied, there is no beneficial effect. So finally, to conclude this talk, I showed that in the model of Strukov and colleagues, external noise has only the effect of degrade the ratio, but in some experiments we showed that external noise can have a beneficial effect. When we move to Pickett's model, we found a very good agreement with experiment results, and found that for small driving amplitudes, noise maximizes this contrast, this resistance contrast. And when large input amplitudes are considered, noise only degrades the resistance contrast. Well, here is the bibliography, and the last slide before lunch is this one.
Thank you, Herman. Nice talk. Is there any question? Yeah.
Thank you. This was just a comment on what he asked earlier about why the switching rate seemed to go down. Was that the question? So that was actually kind of observed in the TiO2 devices. And so you can actually, I know people do current-controlled sweeps most of the time, but you can do voltage-controlled sweeps, and they won't necessarily go out of control. The on state will just kind of saturate. So that was kind of the motivation behind that, I think.
I find this really fascinating, but I'm also kind of confused because this model of Pickett is somehow phenomenological, as you say.
Yes.
And you solve it and it explains the experiments, but is there any way to intuitively understand what's going on rather than just solving these equations? Can you have guessed this answer in some simple way? Or maybe I missed that point,
the answer
I'm
is
sorry.
here when, for example, when we are arranging the input current from here, noise can kick you up to here, and then you can go up to here very easy. So noise helps you to cross the threshold.
Maybe you should go to the questions slide, to the Pickett's model, the previous one, the previous slide, over there. Over there you have two thresholds, right? You have two different, actually three different regimes of behavior for state variable. So noise only kicks you from one regime to the other one.
I see. That's very nice.
So that's actually, it's not a term of Pickett's model or another model.
Well, that was,
That's not enough at all.
yes, that's what I was getting to, because, you know, this phenomenology you may feel uneasy about, but if there is an understanding like that, then you really don't have to worry about it too much.
Yes.
Thank you.
This phenomenon is also observed in many systems where thresholds are observed. For example, electronic devices or electronic circuits, the diodes, transistors, the Smith trigger circuit. So,
Will you try with different kind of noises instead of white noise? I mean, trying to focus on...
It was not.
It was a
wasn't
frequency.
White noise because we have an effective bandwidth.
Okay.
But yes, we are going to try that, I suppose.
Because it could give you information about the patterns
Yeah.
of result and frequency. Okay.
Hi. What kind of equipment did you use to generate current noise?
Okay. Well, that we can discuss on the poster. In the poster.
Okay.
Yeah.
Okay, thanks.
So actually, I kind of understand now that more or less what you were trying to say. So I have just one question. Is this the same thing that people call stochastic resonance?
I don't know if it's a stochastic resonance, but it's something like that. Yeah.
But so that's the
Yes,
idea.
that's the
behind-
idea.
So
behind
you
this.
have these two states, and then you cause
Yeah.
an internal resonance,
Yes.
and you can go between one side and the other.
Yes, there is some effect called dithering, which
Uh-huh.
is almost something like that, but
Okay, so I guess that what you have to do then is to change the frequency of the noise that you want to apply, and then it
yes,
change to.
here we are not changing the frequency,
Yeah.
so that's why not a stochastic resonance, but it's a...
No, but there is something else which is called ghost stochastic resonance. So you actually, instead of you have the noise, and then you have a spatial frequency inside,
Yeah.
and then you measure so you measure the frequency at the outside, and then you can know if the frequency that you are sending at the beginning is at the outside.
Okay,
That's-
yes,
that's good.
yes, I know that effect.
Okay.
Thank you.